All right, today we are starting on page 209. So open up to page 209, and the warm-up says complete all three representations of the polynomial division following the forms of the integer division. So 11 divided into here is 252 with a remainder of 3. So that's why it's 252, and then the remainder is a fraction. So we're going to represent these different ways. So the first thing we're going to do is divide this out. So see, the 2 matches the 2 here. So we're going to divide this out with long division. So 2x squared times the x is 2x cubed. 2x squared times the 1 is plus 2x squared. Okay, that gets you started. Remember, you pick up the red pen and you subtract. Okay, go from there, complete it out. Now you can see that 7x squared minus 2x squared is 5x squared. So there's the 5 right there. And you drop the next thing down like we've done 100 times. Then we say plus 5x. 5x times x is 5x squared. 5x times 1 is 5x. Then we pick up the red pen, we subtract this out. We get 2x. Drop the 5 down. So this isn't going to match 100% at the end. There's going to be a remainder. And based on what you see here, here, and there, we should see a remainder of 3. Well, let's see it. So what do I pick out? 252. Oh, I'm picking out 2. 2 times x is 2x. 2 times 2 is 1. Subtract it off, and we get 3. So this matches this. So what does this mean? The two outside things multiplied together plus the remainder. That's what we're going to do here, is an equivalent statement. So we're going to say x plus 1 times 2x squared plus 5x plus 2, and then plus the remainder. All right, so this mimics this. The remainder is always a fraction, so the answer is 2x, the quotient, right? The answer up here is 2x squared plus 5x plus 2, and then what remains? Well, what remains is 3 out of, not 11, but x plus 1. So there's the answer written this way, and then the division. So it's all connected together. All right, now we're going to look at end behavior. So we're going to look at these examples here. Focus our attention to the g function and the m function here. We look at the degree of the num, which is the numerator, and the degree of the denominator. So let's focus on the first and the last one. The degree of the top, right? Well, there's an invisible x to the 0 up here, so that would be 0. The degree of the denominator is 1. Anytime that this is smaller than this, okay, the end behavior has a horizontal asymptote of y equals 0. Y equals 0 is the horizontal asymptote. So look down here. 1 versus 3. So the highest power on the top is 1. The highest power on the bottom is 3. So it's 1 versus 3. So who wins? The denominator. So this is also y equals 0. A-S-Y-M-P-T-O-T-E. You should be impressed. A-S-Y-M-P-T-O-T-E. This has to do with the whole pizza thing. If you have 5 over a huge number, it's basically 0, so it levels off at 0. The same thing here. If you're comparing x, right, the leading term here versus the leading term here, x versus x to the third, and you get really large numbers in here, this grows so much faster than this, it basically levels off at 0. Now, so that's when this is smaller than this. So when this is smaller than this, it's always 0. When this is smaller than this, it's always 0. Okay? Now we go to the other scenarios. Now there's a tie. The degree on the top is 1, and the degree on the bottom is 1. So then it's 1 versus 1. So these are equal to each other. So anytime it's equal, it's just the coefficients in the front. So it's y is equal to 7 over 1. So it's 7 versus 1, 7 over 1, which is 7. That's the horizontal asymptote. I'm tired of writing horizontal asymptote, so I'm going to write ha! So when it's less than, right, the top versus the bottom, right, the top is smaller, bottom's larger, it's always 0. When it's a tie, you take the coefficients, 7 and 1, 7 over 1 is 7. Now, when it's this way, we're not going to do this one because it starts to get silly after a while. When it's this one here, we divide it and you get a diagonal line. Okay, so that's called, I wonder if they use the term in here. It's called an oblique asymptote, and you get a diagonal boundary line. It's called an oblique asymptote, and they don't use that term in this book. Sometimes they don't use the terms. So we're going to divide this out to see what the oblique asymptote is. And I think this has already been, has this already been divided out? Nope, it's not exactly the same as this. So we're going to divide this out, and we need a place to divide it. So let's, I guess, use this space, because there's not enough space here, so we're going to divide this out. So we're going to do x plus 2, and I'm dividing this one. Divided into 3x squared plus 7x minus 5. So we're going to divide this. All right? And then that'll tell us what the oblique asymptote is. It's a diagonal boundary. So here we are. Okay? And I wrote it up here to divide it. Okay, so what am I picking out? I'm going to help you get started with this. Then we're going to pause, and then you're going to do it. So we do what? Oh, I need a 3, and I also need an x. So you multiply it, put it underneath, subtract it. So do it. And here we go. 3x times x is 3x squared. 3x times the 2 is 6x. I pick up the red pen because I'm going to subtract. We get x minus 5. All right. So this is going to be, I guess I need a 1. So we get 1 times x plus 2 would be x plus 2. Then I subtract it, which means I get negative 7. So I can rewrite this as 3x plus 1 minus, I can do plus negative 7 over x plus 2. So this is the answer, and then the remainder is negative 7 over x plus 2. So I wrote it in this form. That's what they want. So what's the end behavior? Is a y equals 3x plus 1 is a diagonal asymptote. asymptote. So diagonal, I think, is a word you understand better versus oblique, but it's a diagonal asymptote, and it's a diagonal line. All right, and that diagonal line looks like this right here. So the summary of this is when smaller exponent versus larger, it's always y equals 0 is your boundary. If it's a tie, it's the coefficients in the front, so 7 over 1, which is just 7. And then this is be smaller over larger, right? And then when it's like this, we divide and see what happens. So when we divide this one, then we get this number here, which is your diagonal asymptote or oblique asymptote. And then that's just the remainder part that's left over. All right, let's go to the orange page. Here's the orange page. So see, they have this divided to this. So 1 is your horizontal asymptote, right? But it also falls under what I said. 1 versus 1, right? That's a tie. You use the coefficients. So it's 1 over 1. 1 over 1 is 1, and that's your horizontal asymptote. Here, they took this and divided it in here and got this and this. So that's the answer after dividing this. So x plus 7 is your diagonal boundary. Well, there it is. There's your diagonal boundary, x plus 7. Then there's a vertical boundary here because 3 minus 3 is 0. So x cannot be 3 because it's the boundary this way. So x plus 7 is a diagonal boundary. X equals 3 is your vertical boundary. And then the curve goes like that. And that's how this function goes. So when you graph it on the calculator, you'll know what's happening when you type this in. When you type it into a calculator, again, you have to use parentheses on the top and the bottom, otherwise it won't graph it correctly. All right, now you're ready for the purple page.